Hello everyone, welcome to Understanding Physics, in which I'll try to guide you through understanding physics. So today on General Physics 2, we want to start the discussion about relativity, in which it is something that people still forget what it is exactly about. And so in here, I will fully discuss everything that you need to know about relativity. So before we get started, please consider subscribing as well as liking the video, and also check the notes in the description. Check the link in the description for the note throughout this entire discussion. So, let's actually go back to relativity. So, before we go into relativity, we want to ask a subtle question. What is the speed of light? So, you know the speed of light to be c, which is 1 over the square root of mu 0 epsilon 0. But the speed of light doesn't really depend on where do you look at it. It's always, the speed of light is always c. So this is not really relative to anything. So we will discuss some myths that exist before, and we'll try to disprove it. So we will actually discuss about the idea of the ether, which is a imaginary material that carries out the propagation of the electromagnetic wave. And this doesn't exist. And I will show you why. If you have ether, and then if you have this ether to be the source of the light propagation, this would mean that you could measure its velocity relative to the Earth. So we could try to do that. So maybe let's think about a question. Maybe so if you have rain as well as if you have an umbrella as well as some rain, it will fully cover you if you put it directly upwards. But if you move at a certain velocity, you need to tilt it sideways so that your body will be covered. And this is because relative to you, the rain is going to look like this. So you need to cover it at this normal angle again. And so the question is, maybe the ether moves with us. So the ether doesn't move with relative to us. And so we could try to think of this experiment. So there will be this rain here, and then it will later gonna diffract. It will refract into something like this. So that's the idea of thinking of the ether dragging with us. And let's see if this is true or not. So in order to prove this, we could just do a observation of a star. And then you would have Earth moving in this direction and moving in this direction. Or pretty much, if this is your orbit, you could pretty much determine if you're going in the positive direction or the negative direction. And so if you try to observe the light from the star towards the Earth, you would need to put your telescope to be sideways in order to capture all of the light. But it has a different angle if you are measuring it at the other side. It will be something much more like this. So it will point at a different direction. So this gives a clue that to measure light, the ether doesn't move with us. And so if the ether moves with us, you would be putting your telescope to be something like this, which is not true in here. So this proves that the ether will move relative to us. But if the ether moves relative to us, we could do another experiment. Maybe we could just put a interferometer, and then you would have something like this, and then you would have length. And then you would have a mirror, and then you're sending this back. So, because of the movement of light is relative to the ether, this would mean that there is this thing called as the relative motion of light with respect to the ether. So maybe the actual light goes in this direction, but then you would have the ether wind to be moving in this direction. So you would have the total length to be in this direction. And so the time it takes would be, for the one that's going perpendicular to the ether, to the wind of the ether, is gonna be 2L. So the size length is L, and then you divide it by the magnitude of your velocity with relative to the ether, and that's gonna be, oh sorry, it's the light with respect to us, so it's not with respect to the ether because the ether is moving as well. So it's gonna be the square root of c squared. So this is the speed of light, and then this is the speed of the ether that you're trying to measure. So it will be something like this, and this is for the one that's perpendicular. But if your light is going parallel to the ether, to the wind ether, you're gonna have L times c minus v. So the one that's going here, subtract that by this one, so this will be your actual length, and then there would be another one that's gonna go like this. So it's building up like that. So this will be plus L c plus v. So this would be c squared minus v squared of 2cl. And so you could see here that there is difference between the speed of light. And now this difference within the speed of light would later be measured from the interferometer. But this is not true. And it turns out that this is not the case. And so this means that the ether does not move relative to us. So this brings the conclusion that ether does not exist. And this is one of the greatest catastrophes when it comes to science, is that we are trying so hard to find something that doesn't even exist. So instead, what we will do is that, so because of this ether does not exist, there is a very simple idea that you could actually bring up even from the Maxwell's equation, and that is special relativity. So the idea is very simple. So the idea is very simple. Physics always works. In every inertial reference frame. So what does this mean? This means that if you are moving at a certain speed velocity, your observation is as valid as those who is stationary. So no matter if you move or not, your physics should be the same, which means that your speed of light must also be the same. So this is the key idea of special relativity. So then with this, we could actually try to do a very simple experiment. If we have someone looking at light bouncing back and forth and measuring its time, how fast will it take? As long as you know what the length here is. So it's very simple. You could figure out that the change of time would be twice the length because it goes back and forth. Divide that by the speed of light, c. So we'll call this reference frame as prime. The one that's moving. Sorry, the one that is looking at the light, which is also moving with him. But maybe if we actually think of another case, where instead this box is going to move at a velocity called v. how far, what will be the time that will be measured from the person outside. So this uses the same physics. So we have the same length, and then the speed of light must be constant. It doesn't depend on the observer. So that means that the path of light would go something like this. So the total time that it takes would be the length that the light takes, which is the length squared, plus the v over the change of time squared, twice. Divide that by the speed of light. So with this, we would actually try to solve what will be the delta t prime in terms of delta t. And we see that there are two different values. So let's solve this. So we can put delta t here to be, sorry, this is the square root. So we could just put the c inside. So this will be the square root of 4l squared over c squared plus v delta t over c squared delta t squared. Square everything, you get delta t squared equals to delta t prime squared plus v over c squared delta t squared. That means the delta t prime here is delta t to the square root of 1 minus v over c squared. So this is a very useful observation. We see that if you change, so if you are measuring the time from a stationary point of view, looking at something that's moving, it will be as if that, so it will be that your clock will have different values. It is as if the one that's moving has a delay, has its clock to be much more fasted. But even though the clocks are the same and there's no dysfunctioning, this always happens. But you could also think of the other case. Maybe instead of observing it from the one who is stationary, maybe we can observe the second guy moving with relative to the first. And it'll be as if that guy has a clock too early. So this is this is not intuitional. It's that if you have S as well as S prime, this guy observed this guy to have a earlier time. But S prime towards S also says that they're looking at an earlier time. And this is very interesting about relativity, is that every single measurement that you do is relative to where you are looking at it. So starting from this point and going forward, we don't care about time to be simultaneous. You have your own time, I have my own time. And this is one of the key ideas of special relativity. So this is something you call as time dilation. But we should also think about another thing. What is the speed of light? The speed of light must be constant, right? That means delta x over delta t must be the same thing as delta x prime over delta t prime. So if you put this in again, what you obtain now is delta x to be square root of 1 minus v over c squared. And this is what you call S-length contraction. So not only your time changes, but your position changes. So even though if you are holding the same 1 meter stick, one guy will see the other guy holding a 0.8 meter stick instead, and vice versa. So nobody is holding a stick which is longer than the other. It is as if that my ruler is longer than yours and your ruler is longer than mine. And this is a very beautiful idea of relativity, is that even though you use the same physics, but the way that you define your position and your time literally depends on where you're observing it from. So we can just think of a very simple example of this. Let's say this is you looking at two different rods or rulers, and they are moving at certain velocities v towards each other. So when the objects are within the same x direction, you would see two events. One end hitting the other and the other end hitting the other. This is E1 and this is E2. But let's say if you observe this from, let's say, from this tech's point of view, and seeing this object coming through with a much more greater velocity. But the length is less, because as you know, from length, contraction. So what you would observe first is that it will be event 2 that's happening first, and then after that a certain period of time before event 1 happens. But according to the other stick, it's the other way around. You do event 1 first, and then you do event 2. So we now know that our time frames are literally different. We don't know whose time is correct when you're dealing with faster moving objects. And so we need to find a way for us to transform from one coordinate system to the other. And this is where the Lorentz transformation comes in. So the Lorentz transformation is stated that pretty much so this is if you're moving with a very slow pace. You could write one position to be x prime plus vt. So let's say if this is your coordinate system, and then you have another object which is traveling at the speed v. You could know that if this is your 0 and this is your 0, that means that you could transform it between those two coordinate systems. It's x prime plus vt. But if you're talking about higher speeds, we'll just do an example. Let's just say x equals to gamma x prime plus vt prime. So it's the time and the position relative to the second guy which is moving. So this will be our coordinate system. So this will be the relative towards s and then the one towards s prime, which is moving. But this idea should also work the other way around. S prime should observe s to be moving at a velocity v. So this means that x prime should be gamma x minus vt. So the observation now states that these two has to correspond to the same equation. So now what we could do is that with the relation that x must always equal to ct, which comes from the rule of special relativity, what we could get from here is multiple different equations. So we can observe ct prime must equal to gamma c minus vt ct. And so we could get the relation between t prime and t as well. So ct prime must equal to we could divide everything by c. This t minus v over c t. So this obtains t prime over t, which should equal to gamma times 1 minus v over c. We could also do the same thing for the x equals to x prime plus vt, so vt prime. So we'll obtain ct equals to gamma ct prime minus vt prime. This means, sorry, this is plus. So this means that this is t equals to gamma 1 t prime plus v over c t prime. So t prime over t is pretty much gamma 1 over gamma, sorry, 1 plus v over c. Now these two has to be the same thing. Therefore, gamma squared is 1 minus v over c squared. Equals to 1. Yeah. So gamma is 1 over the square root of 1 minus v squared over c squared. And that's what gamma is. We could also try to solve what the t and the t prime relation. So with this, we could actually just substitute your x prime in. So x equals to gamma gamma x minus vt plus vt prime. And so you could write this as x equals to 1 over 1 minus v squared over c squared, x minus vt plus vt times gamma, vt prime times gamma. So trying to gather up all of the terms, you could get the vt prime gamma to be equal to, so there's the x minus this guy, it's gonna be v squared over c squared negative over 1 minus v squared over c squared times x plus v over the 1 minus v squared over c squared times t. So we could divide all of the v's in order to obtain t prime gamma to be equal to minus v over c squared, and that's gamma squared, times x. And then you add this with the gamma squared t. So rearranging everything, t prime is going to be t gamma, multiply that by t minus vx over c squared. And this is the Lorentz transformation for the t's. And so you could also get your t to be gamma t plus v x prime t prime plus vx prime over c squared. You could do the same computation, or you could just observe the relativistic motion. So now with those two, we could solve what is the relativistic motion, or the relativistic velocity addition. So in order to figure out what is the delta x over delta t, or pretty much your u here, you could just use the same equations and try to figure out what's the delta x and delta t. So we'll just use from delta x from the s prime into the s transformation. So it will be gamma delta x prime minus v t prime, divide that by the gamma t delta t prime minus v delta x prime over c squared. And this is gonna solve into, so you could just divide top and bottom by delta t prime. You could get gamma of the u prime minus v, divide this entire thing by the gamma 1 minus v over c squared times the u prime. So the relation is u prime minus v, divide that by 1 minus u over c squared u prime. Sorry, these things should be positive because we are using from the s prime to the s. So everything should be positive, like so. So you could do the same computation, but in the reverse order, like from u prime to u. That's also possible. But this is something that you also need to remember: is that the direction actually matters when you're talking about relativistic motion, because it could be additive, it could be subtractive. So the way that I normally remember it is that x equals to x prime plus vt prime gamma corresponds to object x stationary and with x prime moving with the velocity v. And same thing for the t, it's gamma x plus v t prime vx prime over c squared. So this is how I memorize it, but obviously all of the memorization is up to you, but this is how I do it. So because of this, we could actually bring up the question, is everything relative? The answer is almost true. So there are certain quantities in which it is not changing towards relativity. One of them is the speed of light. But another is something which we call as the spacetime interval. And so this is defined to be delta s squared to be equal to c squared delta t squared minus the delta r squared. So delta r squared literally means your positions. And it turns out that the relation between time and your space doesn't actually change at all. So there are more other types of variables in which they are relativistically invariant, in which I will introduce along the way. So because of this, we actually observe that if you add out all of the u's together, you figure out that momentum isn't conserved. And it is because after all this time, we have been using the wrong formula for momentum. So instead, what momentum exactly is, it's actually gamma mu. So it literally depends on the perspective that you're looking at this at, but also at the u, in which the u is the speed of the actual object. No, sorry. So the gamma here is actually 1 over the square root of 1 minus u squared over c squared. So for very small amounts of u, the momentum is proportional to the mass as well as the u. But when you come to higher speeds, there will be a higher and higher momentum, in which the graph will look something like this. It will go up, so it's linear, and then it will blow out. And this blowout here is the cause of maximum to be speed of light. So anything couldn't travel faster than speed of light. It's a boundary, and it is because of the conservation of momentum. If you want to increase it to be the speed of light, it means that you have infinite momentum, in which where do you get that from? And why does light travel at the speed of light? And it is because that light itself doesn't have any mass. That's the main reason why. So because we know what the momentum is, we could actually derive straight away what the force is, which is the dp over dt. So let's just do the integral. Sorry, the derivative. This is gonna be, so you could just use the chain rule, but I won't fully derive the product rule and the chain rule. And so I won't fully discuss the actual derivation step by step, but in here I will just give you the final answer. It will be gamma cube m du over dt. So this is the definition of the force if you do the derivative straight away. So it's just the product rule, and then there's lots of things cancel out, and this will leave you with this. And if you do the integral, so with respect to x, which will give you the kinetic energy, is the integral of the dp over dt with dx. You could actually transform this into your dp, which is going to be your gamma cube m du over dt, and dx is just the speed, which is v times dt. You could cross out the dt here, so this will be the integral of gamma cube m v du. And if you compute this, what you would obtain is, it is going to be gamma minus 1 mc squared. Now this is where the idea of E equals to mc squared is. It's technically gamma mc squared. So E equals to gamma mc squared tells you what is the total energy while E equals to mc squared tells you how much energy it is when it is at rest. So pretty much any object already has energy, even though if it's moving or not. And this energy is mass. So mass and energy are correlated between each other. It's E equals to mc squared. And this gamma minus 1 corresponds to the kinetic energy of your object. So if you chuck it, it has the energy gamma minus 1 mc squared. And if you actually take very small gammas, or gammas very near to 1, in the end what you would get is half mv squared, which is what you normally observe. So with this, what we could do is that we could actually correlate between the energy and the momentum now. So let's actually try to do that. We can say that the P here is gonna be mu over the square root of 1 minus u squared over c squared, while the energy is mc squared over the square root of 1 minus u squared over c squared. Let's actually square both of them. So you would get p squared equals to m squared u squared over 1 minus u squared over c squared. And in here it's e squared equals to m squared c to the power 4 over 1 minus u squared over c squared. So what we could do here is that we could actually solve the u with respect to p. So we could just solve this here. It's going to be p squared 1 minus u squared over c squared equals to m squared u squared. So this means p squared is the same thing as u squared of p squared over c squared plus m squared. So you could plug this into your e squared here. So what you would get is that the e squared is gonna be m squared c to the power 4, divide that by 1 minus p squared over p squared plus m squared c squared. Yes. Sorry. Yeah. So this will equal to m squared c to the power 4, divide that by m squared c squared over p squared plus m squared c squared. So this is going to be p squared c squared plus m squared c to the power 4. Or pc to everything squared plus mc squared of these things squared. And this is the relation between momentum as well as energy. So it looks like that the relation between kinetic energy as well as the rest mass is like a Pythagorean theorem. And this gives you the relation of the energy and the momentum in terms of the space-time space. And so this is the main reason why space-time interval is invariant under it is relativistically invariant because of this condition. So another thing to discuss about is the electromagnetism. So I won't fully derive the exact equations, but we could do a thought experiment. So if you have, let's say, positive charges at certain spaces going in this velocity v, and then you have negative charges going in the other direction. You would if you have a positive charge here, and then you would see this wire that's carrying positive and negative spaced out evenly. What you would see is that there is going to be a magnetic field within this direction, which means that if you are chucking your, that means if you're chucking your proton at this direction, it's gonna have a force going downwards. But according to relativity, all of the laws of physics should still work, even though there's length contraction, there's time dilation, and which we'll consider now. So instead, we'll just have this proton to be at rest. What will happen? Well, first, the positive charges are going to be much more spaced out, with velocity much more less than the actual velocity. So with this reduction of the velocity, based on the Based on the length contraction, this would be much more longer. But for the negative charge, because it's opposite, the velocity is much more greater, which means that it's going to be much more constricted. So according to your proton, it is observing a surface charge. It is observing that there is charge within this wire, which means that it wants to attract. So there's an electric field, which means there's also a force. And this is the relation between the magnetic field and the electric field. And the fact is, because of the electric field, it causes the magnetic field is because of relativity. If relativity is not there, magnetic field doesn't even exist. Or the idea of the magnetic field is very absurd. So this is why there's a connection between the electric field and the magnetic field, because it is the same idea. So finally, I want to talk about general relativity, in which I won't fully discuss the maths, but in here I want to introduce what general relativity is. So instead of special relativity, in which the observer needs to move at a constant velocity, instead you could have this observer to move with acceleration. And it's totally fine as long as you're doing general relativity. And why is this important? Is because there is this frictional force. So let's think of this condition. If you have a ball falling down, compare that if you have a rocket at space traveling with acceleration, your ball also feels gravity. So this means gravity is relative. So it turns out because of this relativistic motion, what we could state is that space-time is actually curving. So space-time curvature exists. And this is what causes gravity. So because of this space-time curvature exists, we could start to talk about what is black holes and what's a neutron star. So a neutron star is a star in which it's so dense that it has a very high gravitational field, such that the escape velocity, which if you remember is the velocity that you need to escape its force, is pretty close to the speed of light. This is what you call as a neutron star. So it pretty much means that the light almost didn't make it out of the planet for us to see. But this is very different if you look at a black hole. So this is a neutron star. But for a black hole, the escape velocity is far greater than the speed of light, meaning that anything that approaches it couldn't escape anymore. And this is why you have something that you couldn't really see, because the light doesn't get to you because it doesn't have enough velocity to escape its grasp. So because of the space-time curvature existing, that means that if you send light into space, the light could bend, meaning that you could get focuses, and thus you could make those into some form of lenses. And also, because of the space-time curvature, you could also create gravitational waves. And so one thing that is interesting is that there was a observation of black holes emerging, thanks to the idea of gravitational waves. So how do you detect these gravitational waves? So gravity pretty much affects space-time curvature. And if you affect space-time curvature, means that you are pretty much changing distances. So remember when we talked about the Michelson interferometer? If we actually change the positions, it will cause observations, right? But now, if we think of the distances change because of gravity, it will later produce interferometer. There will be interference that you could observe. And this is how you could actually see gravitation. It's so amazing. But that's all about relativity that I'll be discussing here. So So I know that this topic is very unintuitional, especially since you are not able to see this. And even for me, I don't really deal with relativistic motion because most of my field focuses on something much more quantum-like. But this is my best discussion of relativity. So thank you very much for watching, and please like and subscribe, and also please share this to your friends who really need to understand physics in a much more deeper understanding. So thank you very much, and I will see you on the next video.